Welcome DC Circuit students. In this mini lecture we'll be going over the mathematics associated with an RC circuit that's subject to switching. And in particular we're going to look at a case where we have a voltage source with an on-off switch and a second voltage source oriented in the opposite direction, going to ground there, with its own on-off switch, connected to a resistor and a capacitor to ground. So we have a resistor with value R, we have a capacitor with value C, and we have two voltage sources and they are equal. So depending on which way we have the switches, open or closed, we can flow a current in either direction. In this case, conventional current would flow through. We'll call this source number 1 and source number 2, but we'll say that they are effectively equal in magnitude. We could put an absolute value line around that. Just note that they have the same magnitude, but obviously they're hooked up in opposite directions. We'll put a little plus. So if we have voltage source E1 enabled, we're flowing conventional current basically in a clockwise direction, and if we were to close voltage source 2, open voltage source 1, we would flow conventional current the opposite direction. Now, from the point of view of the way we would achieve this in an experiment, let's get another color here. We could use our picoscope or any oscilloscope function generator combination, a function generator for whom we would view the signal with our oscilloscope, of course, and we could create a periodic square wave voltage signal. So we would start with a voltage equal to 0, and at some point we would go up to our maximum, and for whatever period duration dependent on the frequency, then we would go to negative, whatever our amplitude was, and then come back up. And that would represent one waveform when we got back to here. So we would initially go to, we'll call this E1, and then negative E2, and of course if E1 equals E2, we would have square wave. So if we were to look at the transient response of our RC circuit, we can see that, and I'll use another color here, if we were to look at this point as our initial time, which would T0, when we basically closed this circuit, and I need to make a change to my circuit here. Obviously this wouldn't work. Let's make a little change and put that switch somewhere else. We got to put it down here, don't we? Doop. Put a real little switch. Okay, so now we can complete the circuit and run these independently. Apologies for that. So the two switches can work independently, theoretically. So we're at T0, we're going to have our source 2 switch open. We're going to close our source 1 switch, and the voltage that's applied to this point here, we'll call it node A, is E1. So we would expect a transient response of voltage on our capacitor if it was initially discharged, and we can sort of write Q at T equals 0 equals 0. So V sub C at T equals 0 equals 0. As we know, once a capacitor is going to act like a short when we have a very fast change in voltage, which definitely a step function would be. So we'd have all of our voltage drop over the resistor. But as the capacitor accumulated more and more charge, it would start to effectively push back, and we would end up looking at its responses coming up very quickly and then leveling off, and at steady state the voltage, we're going to call this line is our V sub c, which is a function of time. So at t approaching infinity, steady state, then the voltage drop over the capacitor will end up being equal to E1, the original voltage source. So here we are. So we will be at this point in our square wave function, that our voltage signal that we've applied. So we can derive an expression for the voltage drop over the capacitor for that scenario. That's pretty simple. And we're going to just go ahead and do that for practice, and then we're going to point out what happens when we, once we've done that, we're going to look at what happens when we open this switch number 1 and close switch number 2. Because at that point we will have defined a completely different set of initial conditions, even though the mathematical expression for the voltage drop over the capacitor is the same. Because those initial conditions at T1 are so different than T0, we'll end up having an effective different expression. And because of that, we'll have a different way of predicting what our time constant will be, and plotting this curve of V sub c going from the top of one edge of our square wave to the bottom. So we're really looking at the difference between a single voltage step of whatever magnitude to a square wave with an amplitude that's twice that of the voltage step. So basically from here to here is basically 2E, which is equal to 2E1 equals 2E2. Because that's a little bit confusing sometimes when we go from our initial derived expression for a single voltage step, closing switch 1, we can derive our expression for how does the voltage drop over this capacitor change with time. We can create that expression for the transient. But then when we go to our proto board and we impose a square wave voltage, which is really the easy way to confirm that in a real circuit, sometimes it's a little confusing when we suddenly have this double amplitude, and we've already charged up the capacitor, and now we're looking at it discharging through what's basically twice the voltage drive. So we're going to step through that. This is going to involve a little bit of calculus. We're going to try to not make that a big part of the focus here, but mainly focusing on the electronics and how Kirchhoff's voltage law and how the definitions of voltage drop over resistors and capacitors ends up defining the time-dependent expression for the voltage drop over our capacitor, which is something we are going to measure on our proto board with a signal imposed by our arbitrary waveform generator or function generator. Okay, so we're going to start with 1, switch closes. So we're going to assume, boom, we've closed this switch is still open, and current starts to flow. And of course I'm going to write current as an expression as a function of time. That's what the parentheses T means. It means current's a function of time. So switch 1 closes. Okay, so what's true? What can we write as true? We know that the voltage drop over the resistor at any time is equal to R, which is constant, times the current that happens to be flowing through it at any time, which is a function of time. We know that the voltage drop over the capacitor is equal to whatever charge happens to have accumulated on it, which will of course be a function of time, that's going to grow with time, divided by the value of the capacitance. And we know that E1, we're going to assume that this is a invariant, a perfect voltage source, so E1 is going to be equal to E1 not time dependent. That stays the same. Not a function, not time dependent, not a function of time. Okay, so let's apply KVL, Kirchhoff's voltage law, between here and here. So we go from ground at 0 volts. We're going to go up in voltage because we're going from negative to positive through this voltage source, an amount equal to E1. Then current's flowing in this direction, so we're going to experience a drop in voltage equal to the current, whatever it happens to be at that time, times R. So this is going to be minus R times I, which is of course a function of T. Then we're going to drop voltage over the capacitor. How much are we going to drop? Well, it depends on how much charge is there, divided by the capacitance. And that brings us back to ground, which is 0. Okay, now here's where we're going to apply a little bit of calculus. We're going to, and for those of you who have not taken calculus, just bear with me. We're going to use this to create a fabulous algebraic expression which you can put to work, but this way you're going to see how that algebraic expression got there and how it relates to the electronics concepts that are important. So by taking the first time derivative, we're going to mathematically look at how does each one of these quantities change with time. Okay? We've noted that the voltage is the same. This voltage source doesn't change with time. As it turns out, the first time derivative of something that doesn't change with time is 0, because the first time derivative is the rate of change. Well, if something isn't changing, its rate of change is 0. And this was already 0, so the rate of change of 0 is 0. So when we take the time derivative, we get 0 plus 0. And in this case, we're just going to write R times, and this is a symbol for the first derivative of current with respect to time. And we know that the rate of change of charge with respect to time is in fact the definition of current. So if you think of charge as being in coulombs, current is in amps, amps are coulombs per second. So the rate of change of charge with time is current, and let's see which way it's flowing. So in this case, if the charge accumulates, so the rate of change of charge is positive, we're getting more and more charge piling up here with time, that indicates a higher current flow. So we can say that the rate of change of charge on that capacitor with time is equal to the current flow. If the capacitor were discharging, it would actually be negative. So that becomes important when we start looking what happens at T1 forward. But for now, when we take the first time derivative of this expression, we're going to get just current divided by capacitance. So that all equals 0. And I haven't written as a function of T and for each of the currents because we already know those are changed with time. So we can rearrange this. This is, for those of you who might be taking some math in the future, this is known as a variable separable differential equation. It's the easiest one to solve because all we do is rearrange things and we get all of the I and I dependent terms. So we're saying 1 over the current times the rate of change of current with respect to just itself is equal to negative and rate of change of time, and we end up with R and C in the denominator. Those of you who have taken integral calculus will know that we can turn, this is a differential equation because it means we've got an equation, but it's in terms of the rates of changes of things. We want an algebraic expression, so we can just say, you know, current, time, we want an expression. As it turns out, we can solve this differential equation by applying the opposite of a derivative. We can take antiderivatives or integrals. And it just so happens that the integral of 1 over anything with respect to that anything is the natural log of that variable. And as it turns out, the integral of a constant with respect to something is just that constant times the variable. And anytime we integrate, we end up throwing out some constant, because you could always take the derivative of a constant and get 0. The rate of change of something that isn't changing is 0, which we saw over here. So here's our algebraic expression. The natural log of the current, which is going to change with time, flowing this way through the circuit when we close switch 1, is going to equal negative times time, however much time has passed, divided by the product of the resistor and the capacitor, whatever those values are, plus some constant. Now it's much easier to manipulate this and think about it if we get rid of the natural log term. So we're going to do that by taking the exponent function of both sides, which is the inverse of natural logs. That gets rid of the natural log, and we end up with the exponent of everything on this side. Take the exponent function of it. Take the exponent function of it. So with the exponent of natural log of I is just I, because exponent and natural log are inverses, they undo each other. The exponent of this term we could write as exponent of negative t over rc plus k, but one property of exponents, for those of you who have taken some algebra 2, a little advanced algebra, you know that you can express the exponent of a sum as the product of the exponent of those two the two terms in that sum, the two addends. So we can write this as k. Really it's exponent of k, but the exponent of constant is just another constant. So we get k exponent of negative t over rc. So if you've studied transients of our RC circuits in any of your electronics textbooks, this will probably start to look familiar. So the current flowing through the circuit is some constant times the exponent of negative t over rc. The exponent, the negative exponent function, decreases with time. So if I were to draw a little, I over t, it's going to be something like this. So the longer the time, the smaller the term's going to get, which makes sense because this is going to the capacitor is going to charge up, start creating a back voltage that eventually will be equal to the source, and if the two sources are equal, there's no drive for current to flow. Eventually it'll just stop. Now, when it'll stop, we got to evaluate this k. And for that, we need to look at what's going on when t equals 0. Okay, so at time 0, the capacitor was discharged. There was absolutely no charge on it. So that means V sub c, if this was 0, V sub c was 0 at time equals 0. Well, if V sub c was 0, then the current was controlled exclusively by the resistor. So we can just apply Ohm's law. So at t equals 0, I was just equal to E1 over R. So we can look mathematically and say if that's 0, this whole term is 1, and so K has to be E1 over R. So give ourselves a little bit more room here. We may have to redraw our circuit. So we can say the current, anytime after we close switch 1, is going to be equal to that source 1 divided by R times exponent of negative t over RC. Okay, which is great, except when we go to evaluate our circuit, most of the time we're going to want to measure voltage. So we're going to have our circuit set up, and I'll redraw it real carefully, real quick here. We're going to build our circuit. And I'm going to draw it without the switches because I'm just going to assume that we've just got this circuit right now. So here's our capacitor and a resistor. So we're going to end up measuring between ground and that point to give VC. So we're going to hook up our scope probe to this point right here, and it'll automatically measure between that point and ground as our scope, our oscilloscope will, because it's grounded through our voltage source, which in the case of our USB oscilloscope will be through the ground of the computer that's driving it. So this will be a function of time. So we'd like an expression that matches this so we can compare our calculations to what we're measuring. So let's go back to KVL to find V sub C. So we knew, let's go back to our KVL expression. So we had E1 minus IR minus VC equals 0. So we can isolate voltage drop over the capacitor, which is what we'll be measuring in our circuit, is going to be equal to our invariant voltage source minus I, which is that whole expression, so times R. So we have R times E1 over R exponent negative t over RC. So that cancels, and we can say the voltage drop over the capacitor at any time is equal to the voltage that we drove it with, our initial step, times 1 minus exponent of negative t over RC. Okay, so we can take a step back and say, now, does this make sense? Let's start with a shorting condition. We first hit the switch, right? There's no charge on the capacitor, so the capacitor should act like a short, which means the voltage drop over it should be 0. It's shorted, no voltage drop. So if we take t equals 0, so let's make sure the math matches what we know the electronics should do. So if t were 0, this term would be 1. 1 minus 1 is 0, so V sub c equals 0. So that checks out. Now we know that eventually we'll get a charge on this capacitor that is of a magnitude that is the same, that allows Vc to be equal to E1. So basically, Q at t approaching infinity, like a long time, which turns out to be 5 times RC, give or take, is going to be such that V sub c equals E1. So we could solve for the actual charge that would correspond to that. So let's take a look at our expression. I'll rewrite it again real quick. So we're going to use again the properties of the exponent function to kind of do a thought experiment and check that out. So we got negative t over RC. Okay, if t gets huge, then what we know about the exponent function is that this, as t gets really, really big, the exponent function, t exponent negative t on the y-axis, looks like that. So the bigger t gets, if there's a negative sign, the more this whole term will approach 0. So as we get out to a long time, which would correspond to steady state, the voltage on the capacitor T approaches infinity equals E1, which checks out based on what we know. So what we know is that if we have a circuit, and we're going to go back up here, if we look at the first step of our square wave, we know that when we get to this point, we have a charged capacitor. We've got an expression that can predict this curve up to C1, and we can predict a time in that curve that we could evaluate R over C. And when we go to look at our plots from our picoscope, from our oscilloscope, when we apply a square wave, what we're eventually going to want to do is relate the appearance of the curve that we get that represents the voltage signal over the capacitor to R and C. And that product of RC is known as tau, the time constant. And so we're going to eventually want to measure tau and relate that to R and C by measuring it experimentally. Now, one of the problems that we have is that when we apply a periodic signal, we lose this first section because the waveform generator is just constantly giving us this square wave signal. So what we end up getting that we can measure is this part of the curve. And so when we measure V sub C, the voltage drop over the capacitor, we're going to get this green curve. So we're going to lose this first step for which we derived our nifty expression, V sub C equals E1 times 1 minus exponent of negative t over tau. Now we've got this curve, which is a little bit different. And we have two ways to get at that. What we're going to need to do is find an expression for this part of the curve, or this, because that's what's going to show up on our scope. So having derived the expression for our time 0 to T1 here at this upper corner of our first forward-going square wave, we're going to take a break, and then we're going to revisit the circuit. And what we're going to look at, I'm going to use one last color, aqua. We can think of our square wave as being formed by a series of alternating opening and closing of these switches. So we open switch 2 of E2, kind of the backwards battery, we closed E1, but if we open the E1 switch, we keep E2 open, we acknowledge that the capacitor is all charged up. It is all charged up, and it's charged up with a Q that corresponds to a Q over C equal to E1. So V sub C equals E1 at this point right here. Now what happens when we close this switch? Because that's the condition we get on this portion of the square wave, which is what we can measure on our scope. What happens when we now, instead of just going back to a voltage of 0, we double down? Because now, if you think about it, you've effectively got E2 and C that are pushing in the same direction, and current is going to want to flow this way until they've discharged, but they have to flow through the resistor, and they're flowing in the opposite direction now. So what we're going to do in the next video, or after a quick pause, we're going to come back to this, and we're going to derive an expression for this portion of the curve that I am just drawing in aqua, where we have a charged capacitor charged up, so a V sub C equals E1, but now we switch sources and we drive the circuit where we're kind of pulling that current out of the capacitor in the same direction it wants to discharge. And then C what the current and the voltage drop, the voltage across the capacitor versus ground is as a function of time, see what tau is, and then see how we would measure that and confirm it on our plot, which we eventually want to be able to do with a real circuit. So I'm actually going to end this video and I'm going to start another one, and I'm going to redraw my circuit, and we're going to start at this upper corner here of our square wave and look at what happens, create a nice mathematical expression for what happens when we're discharging our charged up capacitor with that second half of our square wave periodic function. And then I'm going to present what's known as a universal time constant scheme, which is something that you can find in Tony Kuffeld's DC circuits book, which will basically be analogous to what we derive and will be applicable for any start to finish condition in an RC circuit. So stay tuned for that second derivation video.